Welcome. Today, we're going to explore a powerful machine learning technique called gradient boosting. It's an ensemble method, which means it combines multiple simple models to create one highly accurate predictor. Think of it like a team of students working on a complex problem. The first student gives an initial answer. The second student doesn't solve the original problem again. Instead, they focus on correcting the first student's mistakes. A third student then looks at the second student's corrections and corrects any remaining mistakes. This continues, with each new student focusing on the errors left by the team before them. By combining all these focused corrections, the team's final answer becomes incredibly accurate. Gradient boosting works in the same way, but with simple models, usually decision trees, which we call weak learners. Let's use a concrete example. Our goal is to predict house prices based on their square footage. Here's our small dataset. Gradient boosting starts with a very simple initial prediction. For regression, this is usually just the average of all the target values. Let's calculate the average price from our data. We sum all the prices and divide by the number of houses, which is 6. The sum is 2,000. And dividing by 6 gives us approximately 333.33. For simplicity, we'll round this to 333. This is our base model, our first guess. Our initial model, F0, predicts 333 for every house. Now, let's calculate the errors, or residuals. The residual is the actual price minus our predicted price. Let's create a table to see these first residuals. These residuals represent the mistakes of our first model. The core idea of gradient boosting is to now train a new model to predict these very residuals. We'll use a simple decision tree, a weak learner, as our next model, H1. We train a new decision tree, H1, to predict the residuals from the last step. Let's say our simple tree finds one split. Is the square footage less than or equal to 1,600? For houses with cubic feet less than or equal to 1,600, we predict the average of their residuals. That's -133, -83, 53, which averages to -89.6. Let's say -90. For houses with square feet equals 1,600, we average their residuals, 67, 87, 117, which averages to 90.3, let's say plus 90. Now, we update our predictions. The new model, F1, is the old model, F0, plus a small fraction of the new tree's prediction. This fraction is called the learning rate, eta. A learning rate prevents us from overcorrecting. A common value is 0.1. So, we add 10% of our tree's correction to the previous prediction. Let's calculate the new predictions and the new residuals. We have new predictions, F1. Now we calculate the new residuals based on these updated predictions. Notice how the errors are getting smaller. What's next? You guessed it. We train another tree, H2, on this new set of residuals. This is the iterative process of boosting. Let's say this new tree, H2, finds a different split, perhaps at 1,900 square feet, and calculates new average residuals for its leaves. Then we would update our model again, F2 equals F1 plus eta times H2. This process repeats for hundreds or thousands of trees, each one making a small correction. After many iterations, say m iterations, the final prediction is the sum of the initial base model and all the small corrections from each tree, scaled by the learning rate. This can be written as our initial guess, plus the contribution from the first tree, plus the contribution from the second tree, and so on. Each weak learner, HM, only needs to be slightly better than random guessing. By adding them up sequentially, they collectively form a single, highly accurate, strong learner. Now, for the key mathematical insight. Why is it called gradient boosting? It's because this process of fitting to residuals is a form of gradient descent. First, let's define a loss function. For regression, we often use half of the mean squared error. This function measures how bad our model's predictions are. Our goal is to change our model f of x to minimize this loss. In gradient descent, we take a step in the direction of the negative gradient of the loss function. Let's compute the gradient of the loss with respect to our model's prediction f of x. We use the chain rule. The derivative of the outer part is 2 times the inner part, and the derivative of the inner part, negative f, with respect to fx, is negative 1. This simplifies to negative 1 times the quantity y minus f of x. A negative gradient, which is the direction of steepest descent, is therefore positive, y minus f of x. Look at this result. The negative gradient is y minus f of x. But what is this expression? It's exactly the definition of the residual we used earlier. Residual equals actual y minus predicted f of x. This is the beautiful connection. Training a new model on the residuals is equivalent to performing gradient descent on the loss function. We are moving our overall model f of x in the direction that best reduces the error. So let's summarize what we've learned about gradient boosting. First, we start with a simple initial model like the average of our target values. Then we iteratively build new, simple models, which are typically shallow decision trees. Crucially, each new model is trained to predict the errors, or residuals, of the combined model so far. We add these new models into our ensemble, but we scale their contributions by a small learning rate to avoid overfitting. And finally, we saw that this intuitive process of correcting mistakes is actually a clever way of performing gradient descent to minimize our loss function. Gradient boosting is used in many real-world applications, from search engine ranking to predicting financial markets, because of its high accuracy and robustness. Thank you for learning with us. Understanding gradient boosting opens doors to mastering one of machine learning's most powerful techniques.